So today we're going to look at our second signature scheme. And so this will be a scheme that's based on the discrete log problem. And so what we're going to do first is actually kind of walk through a naive implementation of such a scheme. And this will kind of motivate the more secure version that we're going to look at. Okay? All right, so the idea would be, so first of all, just establish a discrete log problem in C mod P star, as usual, for some large prime P. So we're going to choose alpha. We're going to choose some exponent a such that GCD of a of p minus 1 is equal to 1. And then we're going to let beta be congruent to alpha to the a mod p, right? So that a is log base alpha of beta. All right, so the idea is Alice wants to sign a message m in z mod p star. And so the idea then would be to send an exponent x such that alpha to the m is congruent to beta to the x. Okay, so the idea being that the relationship between m and x has to be satisfied in the exponents. And so really the only way to be able to find the x that's going to satisfy this for arbitrary m would be to know a. Okay, in fact, we can see that by seeing how exactly we would find such an a. Okay, so beta is alpha to the a. Find such an x rather. So beta is alpha to the a. So this is alpha to the ax. Okay. All right. But then I'm going to assume that alpha is primitive here for the moment. So this is going to be equivalent to ax being congruent to m mod p minus 1. Right? So remember that when we bring down exponents and congruences, we have to change the modulus to be the order of the base. Okay? And then I would want to solve for x, but we assume that a was invertible mod p minus 1, so x would just be congruent to a inverse mod m. Okay? All right, so if we know a, we can find the correct x. Okay? And finding the correct x in general amounts to, right, solving this congruence, right, which we can only do if we actually know the value of a. Okay. All right, so the sign message would be the pair, x comma m. So Alice would send that to Bob, and then the verification will be done by checking that beta to the x is actually congruent to alpha to the m mod p. Okay. All right. However, there's a big issue with the scheme. And the issue is that once this verification checks out, well, then Bob knows that this congruence here must hold. Okay? Knowing this congruence amounts to being able to solve for a. Okay, so from this congruence, you can solve for a. Now, you may not be able to solve for a directly if x is not invertible mod p minus 1, but you at least narrow down the possibilities, right? So this congruence gives a bunch of information about a. So even by signing a single message, Alice is possibly allowing the system to be broken, and then it wouldn't be reusable, right, to be able to do more signatures securely. All right, so the next signature scheme that we're going to look at, so it may appear a little bit complicated, but the reason for this complication is basically we have to do something to get around the problem that we saw with our naive attempted implementation. All right, so the fix is what's known as the ElGamal signature scheme. And so basically we're going to put an additional layer of security here. Okay, so again, Alice is going to set up this discrete log problem in Z mod P star. Okay, so again, publish so alpha, beta, and the prime P, where beta is congruent to alpha to the a. Okay, and a is a secret parameter, so that's known only to Alice. All right, and so every time that Alice wants to sign a message, she's going to randomly choose a different exponent k, again, which should be invertible mod p minus 1. Okay, so Alice is going to choose this k in z mod p minus 1 star, and then use that to generate another parameter r, which is going to be alpha to the k. That should be mod p. Okay. And r will also be, it'll be public, it'll be part of the signature, but k is going to be kept private. All right, so essentially what this is going to allow us to do is use the message and also k, r, and a to calculate another parameter. And we'll be able to do this without revealing any information about a. All right, so the condition that we want to satisfy here is that we're going to put something congruent to alpha to the m mod p. Okay, so just like in our naive implementation where we had beta to the x being congruent to a to the m mod p. But again, this something here will be a little bit more complicated. Okay, so it's going to be this beta to the r, r to the s. All right, so we already know what r is. We already know what beta is. Okay, so beta is part of the overall scheme that Alice has set up. R is something that's going to be generated for this message based upon k. So really all we have to do here is solve for the s that's going to make this congruence hold. Okay, so we want beta to the r, r to the s to be congruent to alpha. Oh, okay, so this, I mean, if we break this up into what beta and r are. So beta is alpha to the a, so this beta to the r is alpha to the ar. R is alpha to the k, so this r to the s is alpha to the ks. Okay, I can write that as a single power of alpha, so alpha to the ar plus ks. And so that should be congruent to alpha to the m. Okay. All right, but again, let's bring down the exponent here. Okay, so that means that ar plus ks should be congruent to m mod p minus 1. And then I want to solve that for s. Okay, so that means that s is going to be congruent to k inverse times m minus ar. And remember, we chose k to be invertible mod p minus 1. Okay. All right, so we can completely solve for s. And then if we use s, right, this chain of congruences can be run backward. And so we can see that, that if we do use this as s, this implies that beta to the r, r to the s will be congruent to alpha to the m mod p. Okay, so this is going to be the verification condition that we're going to use in this signature scheme. Okay. All right, and so then the key thing here then, the reason we're doing this is that we have to put in these sort of two unknown parameters, right? Because again, just knowing this verification, right, is enough to know that this congruence holds. Okay, but if you know this congruence holds, and you know r and you know s, okay, because those are going to be part of the signature, and you know m because that's the message. Well, you still don't know a nor k, so you've got a single congruence with two unknowns. Okay, so that means that a and k, right, could still be anything, right? Or at least anything that's invertible mod p minus 1. Because for any choice of a, there'll be a unique k in z mod p minus 1 star that satisfies this. All right, so you really haven't narrowed down the possibilities for a at all just by knowing that this verification holds, right, because you've got two unknown parameters instead of just one unknown parameter. Okay. All right, so to formally specify this signature scheme then, this is what's known as ElGamal signatures. Okay, so this is kind of just reviewing what we've just said, but putting it in terms of the specification of this protocol. Okay, so Alice is going to choose the large prime p, primitive root alpha, secret exponent a, which should be invertible mod p minus 1, and then it's going to compute beta, which is going to be alpha to the a mod p. Okay, so Alice is going to publish p, alpha, and beta. Okay, so these will be public parameters of this instance of the scheme. So now we've got a message m that we want to sign. And so to sign the message m, what Alice is going to do is select a random k. It's going to be invertible mod p minus 1. Alice is going to compute r, which will be alpha to the k mod p. and then compute S, which will be K inverse times M minus AR, mod P minus 1. Okay. Then, also I should note here that the signed message will be this triplet, then M comma R comma S. Okay, so every signed message contains the original message and then these two other components of the signature, and then verification is done by checking that beta to the R to the S is congruent to A to the M mod P. Okay. All right. Now, so what about forgeries? Okay, so if Emerson, or maybe Freddie, wants to try to use the above method to produce a signature on a specific message M, then knowledge of A is going to be necessary, right? Because they're going to be trying to satisfy the condition. So beta to the R times R to the S is congruent to alpha to the M mod P. Okay, so that's congruent to knowing, finding R and S such that R to the S is congruent to beta minus R times alpha to the M, right? Which, so given, suppose that Emerson fixes an R, then that's going to be equivalent to calculating the log base R of this right-hand side of the equation. Okay, so trying to forge a signature by satisfying the verification congruence means essentially computing a discrete log. Now, one very important thing about utilizing this scheme is that we should never reuse the value of K. All right, so that means that any two different signed messages should have different values of R, because different values of K should be used to actually generate the parameters for that scheme. Okay. So let's see why. So suppose that Alice uses the same value of K to sign two different messages, M1 and M2. Okay. So the same value of K is used, the value of R is the same in both signed messages. The values of S, so S1 and S2, will generally be different. Okay, so we'll have these two signed message pairs that'll look like this. M1 R S1, M2 R S2. But then if you look at the congruence that's used, right, for generating S, right, so we're going to have so S1 congruent to, or let me write it like this, so S1K congruent to M1 minus AR, S2K congruent to M2 minus AR. Right? But the AR, right, is the same in each of these. Okay, so I'm going to have minus AR is congruent to the top congruence here, S1K minus M1. I'm also going to have that as congruent to S2K minus M2. Okay. So we get this congruence. Now we can cut out the minus AR, right, and we can write this as a congruence for K. So we'll have S1 minus S2K is congruent to M1 minus M2, mod P minus 1. Okay. And we could solve this for K. Now, again, so this S1 minus S2 might not be invertible mod P minus 1, so there may be several solutions. But we can find all the solutions. And if there's not too many of them, we can test which one is the correct value of K simply by computing all the values of alpha to the K mod P until R is found. But that just gives us K, which would be no big deal, except that we can actually use K to then solve for A, right? So we can plug K back into this congruence here, and then get AR is congruent to M1 minus KS1 mod P minus 1, and then use that to solve for A. Once A is found, the system is broken, and then the intruder can reproduce Alice's signatures at will. So let's look at an example to see what can go wrong when we reuse the value of K. All right, so suppose Alice sets up an ElGamal system. Prime P is 224, base alpha is 2, prime P is 227, alpha is 2, beta is 224. And so the two messages are M1 is 66, M2 is 26. And suppose the signed messages are 66, 164, 112, because the 82 was a typo. So the correct value of R is 164. And then 26, 164, 110. Okay, so we can see from that that the value of K was reused because we got the same value of R in both signed message triplets. Okay. All right, so that means then that we know, according to our equation above, that S1 minus S2K is the same as M1 minus M2. Okay, so S1 minus S2 is 2. Okay, so 2K is congruent to 40 then. Okay. All right, so this is an instance where we have a non-invertible coefficient. Okay. So we have D equals GCD of 2 and 226, which is 2 many solutions. Okay. And then we can find those by dividing everything through by that D. Okay, so we know K is congruent to 20 mod 113. And so that's the unique solution mod 113, but that gives us two distinct solutions mod 226, namely 20 and 133. 133 is invertible mod 226, 20 is not, so that tells me 20 would have to be the solution. I could also just check, right, plug in and see that alpha to the 133 does in fact give me my value of R, which is 164. Okay, so either way I see the value of K has to be 133. Okay. Again, that wouldn't be a huge problem, except that right, now that congruence that had those two unknown parameters in it is down to one unknown parameter, namely A, and so we can plug everything into one of those congruences and then solve for A. Okay. All right, so remember the congruence that we used to determine S started as M1 congruent to AR plus K S1 mod P minus 1. And so this is using the triplet M1 R S1. Okay, and then I'll just shuffle that around a little bit. So A times R is congruent to M1 minus KS1. Okay, so R was 164, so that's just plugging in for R. And then if I plug in the values corresponding to M, right, so 66 for M1, 112 for S1, and then 133 for K. And that right-hand side should reduce to 86. Okay, so you can check that. And again, I'm in a situation where this is not invertible mod 226, but I can divide through by that GCD, which is 2. Okay, and get 82A is congruent to 43 mod 113. Okay. Turns out that 82 inverse is 51 mod 113, so I multiply both sides by that inverse. Okay, so A is congruent to 43 times 51. So A is congruent to 46. Okay, but again, that's mod 113, so I get two distinct solutions, mod 226. Okay, and so my two distinct solutions are 46 or 159. Okay, and then again, I can just check. Right, so plug those in, and if you do that, you'll see that alpha to the 159 is actually congruent to beta mod 227, and so now I know A is 159, and so the system is broken. All right, so the moral of the story then is never, if you're using ElGamal signature schemes, use a new randomly generated K on each signature, right? So each message gets its own K, and so you would never want to reuse that value, and so each message is going to have a distinct component R. Okay? So if that's the case, you can reuse the same alpha, beta, P as many times as you like. All right, so let's talk a little bit about forgeries then. So similar to RSA signatures, with the ElGamal signatures, it's going to be generally difficult to do selective forgeries, but pretty easy to do an existential forgery. All right, so coming up with some triplet where the triplet verifies as a valid signed message, but where there's no control over the message, right? So the message will just look like random nonsense. All right, so let's see how we might do this. Okay, so the way I'm going to try to come up with an existential forgery in ElGamal is just kind of suppose here that I and j are integers that'll be valid exponents on alpha in the scheme. So they're in the range from 0 to order of alpha minus 1, so from 0 to p minus 2. And so now let's kind of focus on that parameter r, and we can express r in the form of alpha to the I times beta to the j. And why would we want to do this? Well, certainly this can be done, right? In fact, if I think of this as having a j in mind, then alpha generates d mod p star, so there'll certainly be some I for which this has a solution. Okay, so this is a valid way to write R, no matter what your choice of j is. Okay. And then the other reason we may want to do this is then we can put that verification condition all in terms of the bases alpha and beta. Okay, so the verification condition becomes alpha to the m is congruent to beta to the r, and then r to the s, but then r is alpha to the I, beta to the j. Okay? And then if I just collect powers of alpha and beta, then this becomes alpha to the m minus is is congruent to beta to the r plus js mod p. Okay. All right, so again, so if I'm a forger and I want to satisfy this congruence, so again, this looks pretty difficult to do if things are arbitrary, because essentially it amounts to solving a discrete log, right? So if I just pick a j and run with it, then I've got to find an s that's going to make those powers match up, right? That's going to be tough to do if I don't know a, if I don't know what power of alpha gives me beta. Okay. On the other hand, there's an easy way to satisfy this congruence. Namely, just make both of the exponents be equal to 0. Right? So if both of the exponents are equal to 0, that means that I'm going to get alpha to the 0, beta to the 0, and those are both equal to 1. So I actually don't even need to know what power of alpha gives me beta to do that. Okay? All right, so both exponents are congruent to 0, and I get m minus is is congruent to 0. I get r plus js is congruent to 0. Okay. And then given that j is invertible, mod p minus 1, then I can solve these congruences for m and s. Okay, so I want to know what m and s are going to be. And so the idea is that r will be chosen arbitrarily, and then m and s will be given based on that. Okay, so this should be fairly straightforward. So I would just take this bottom congruence, right, solve it for s. So it will be minus r times j inverse. Right? Okay, I'm assuming j is invertible. Right? And then I would just plug that into the top. Okay, so then this one becomes m plus minus r ij inverse. Okay, but then I want to solve it for m. So that would be minus r ij inverse mod p minus 1. Okay. All right, so the point is I could pick I, j, and r to be whatever I want. M and s would then be determined, but then I would get a pair of a triplet that would satisfy the. Well, okay, sorry, I have this congruence, right? So R is determined from this congruence up here, but I could pick I and j arbitrarily. R is determined from this. M and S are determined from this, and I get this valid signature. Okay. So here's just a little example. So suppose Alice sets up an ElGamal signature scheme. P is 1223, alpha is 5, beta is 590. Okay, so here's how I might do my forgery. Just randomly choose these I and J, right, which just should be numbers in Z mod, or numbers between 0 and P minus 2, such that J is invertible. Okay. Then R would have to be alpha to the 38, beta to the 51, which is 269. I would compute J inverse, which is 623. Okay, so then S would have to be, so minus R times J inverse, okay, which is 1049. Okay, then M would have to be so minus Rij inverse, okay, which is going to work out to 758. Okay, and then so 758, 269, 1049 would be my valid signed message. And then you can verify that by checking that alpha to the M and beta to the R times R to the S are actually both congruent to the same thing. Okay. All right. However, once I picked I and J, and then this M was at the mercy of what all the other parameters worked out to be. Okay. So in general, the best you're going to get is that the M will just be some random looking nonsense. So for that reason, it's an existential forgery rather than a selective forgery. All right, so that's it for today, and we'll look at one more signature scheme.